Good morning, everybody. Today, Codeforces round 658 is going on. This was written by Monogon, and I helped test it, so obviously I can't compete, but I thought it would be helpful for me to offer some solution ideas to some of the problems that I know how to solve, in case you're looking for those. So we'll start with div 2. The easiest problem is common subsequence. In this problem, you've got two arrays, and you want to find some third array that's a common subsequence of both. If there are multiple possible answers, you want to find the shortest one, and that should be quite a big hint. And if there are multiple possible shortest ones, you can print whatever you want. So let's say you've got some arrays here. Let's use maybe a more pretty color than that. Let's use like white, and then we can do a lighter blue. How about that? So if your arrays are maybe like 5, 3, 1, 4, 4, and maybe it's 1, 3, 4, 7, 2. Then one common subsequence you could pick would be 3, because 3 occurs here, and also it occurs here. If you have some subsequence like 3, 4 that's too long, that works as well, but you want to find the shortest one, so you can always just take any common element in both. You can do this really easily just by using a hash map. So if you have a hash map of all the elements in the first array, you just see if there are any elements in the second array that also are in that hash map. Awesome. So that's problem A for div 2. About as easy as you might expect a problem A to be. Let's move on to problem B, sequential nim. So in this game, there are n piles of stones, and the ith pile has some number of stones. On a given turn, it's a lot like nim. You can take as many stones as you want from a single pile, but you have to take it from the first pile this time. That makes it different. So why does that matter? Well, you have this interesting result now, which is since the only pile that you have to take from is going to be the first pile, then you really have very few choices. Really, you just have two choices. That's it. So let's say you have some number of piles. Maybe they look like this. Maybe these are the piles here. Now let's consider like the rest of these piles. If we were to play the game on these piles, someone would win, right? Maybe this is a losing state. So if this is a losing state, you want it to be your opponent's turn when this pile is taken, which means you need to take this entire pile. Now, that's one possibility. The other possibility is, what if it's a winning state? That is, I guess, also quite possible. So what would that look like? Instead of making it a losing state, maybe this is a winning state. So in other words, if you were playing the game on just these last 4 piles, if you would win, then you want it to be your turn when this gets taken. So what you can do is you can take all but the last stone in this pile. And now when this stone gets taken, then it's your turn and it's a winning state, which means you'll end up winning the game. So essentially what this means is the first person to move in this game gets to choose who the winner is. They get to choose who gets to take the last pile. Now, it could be slightly different because what if we consider this case? Well, in this case, the first person who goes doesn't really have a choice in their move at all. They just have to take this first stone. So what we can do is we can, special case if there are all piles of 1s. Otherwise, if there are any piles that aren't 1s, whoever gets the first pile that isn't a 1 is the person who gets to determine the winner. So if that person wants to win, they can win. If it was a Misere version, they could also choose to lose. Very cool. All right. Cool. So problem C. Initially, when I was testing, this was just one problem. And I think it was thought to be easier than the testers wound up making it look. I saw it right away. I had like a solution that wasn't intended. So I'll talk about my solution because I think mine's pretty neat. So let's go over the problem first real quick. You've got some string. Maybe it looks like this. And then you want to make it into some other string. And what you can do on a given turn, you can take some prefix like this. Then you can reverse the prefix, so it's like that. And then after that, you can invert each character, so it looks like this. So those are the 3 things you do on a given turn. You can only do it for prefixes, you can't do it for any substring. And the question is, how do you make this look like that? How do you turn A into B? Well, there are a couple things you can do. You can do like you can maintain like a substring in the middle. I think that's the intended. Might be in the editorial if you're interested in that solution. But alternatively, you can come up with another really cool solution. And that solution is just, let's turn it into all zeros. Once we have all zeros, let's turn it into this. So it should be pretty easy how you could turn this into all zeros. What we can do is, if we have some string that looks like this, first we can turn this into ones. Now we have all ones. Now we can turn this prefix into all zeros. So if we flip these, then we'll have a bunch of zeros here. And then after that, we can make, well, then it'll look like this, right? So then after that, we can make these be all ones. And the important part here is we don't actually need to concern ourselves with the reverse operation happening, because since it's all one character, it's a palindrome, so the reverse part doesn't affect us. So really, all we're doing is we're like changing each character, and that's all you need in this case, because if all we're doing is turning it to all zeros, that's very easy. Cool, so we know how to, oh, sorry, I guess there's one more step. Once it's all ones, you just change everything to be all zeros. So we'll do one change, at most we'll do one change after each index. Every time it changes from a 0 to a 1, we'll do one change at the end. And you can imagine putting a 0 at the end here to make it easier to implement. So what you can do if you want to actually extract what the steps are, you can turn this first string, the top one, into all zeros. And then you could imagine turning the second string into all zeros. But then we'll just do these operations backwards. And that's it. So if we do the operations in the reverse order, it'll turn all zeros into all ones, because the operations are, I guess, reflexive, symmetric. Cool. Okay, so there are two more problems in Div 2, but these are also, we're in the shared with Div 1 version now. And I think it's pretty cool here. So problem D is unmerge. I really enjoyed this problem. Initially when I did it, the bounds were 10 to the 5th and everything. So it was a little bit harder. So I'll go over my solution to that. I cheesed it originally. I came up with an unintended solution, and now they let that pass. So here's the idea. So you've got, like, when you do merge sort, you have two different arrays. So maybe you've got like this array here. You also have this array here. And you need to combine them. You need to combine them into one big array by merging them. So with merge sort, maybe you take this first element for this first index, then you take this one, then you take this one here, then this one here, then this one here, then you take this. Maybe you do something like that, and then you fill out the entire array. At each step, the way merge sort works is you compare the first element in this top queue to the first element in the bottom queue. And then whichever one's smaller, you put that in the new array. So with merge sort, the way the algorithm works, you're only doing this with sorted arrays. You could also do it with unsorted arrays, and that's what the problem's asking about. So they're asking, in particular, if you have some finish array, which I guess, what was the example they used here? They had a pretty good one. 2, 3, 1, 5, 4. Let's add a sixth element to that. So let's say 2, 3, 1, 5, 4, 6. So maybe this is our array. And okay. So now let's say we want to we want to have this array, and we want to like split it up into two separate groups, where each group, if you merged these two groups, you would have the original array. So that's the idea behind the problem. There are a couple observations that we should probably make before we try to actually find a solution. And that is, let's look at this part right here, this 3 and this 1. What we know is, we know the 1's smaller than the 3, obviously. But this like creates an interesting observation, which is these things have to be from the same group. If you had a 3 and a 1, right? If these were the two front parts, you would have taken the 1 first instead of taking the 3 first. But we didn't, we took the 3 first, which means the thing that was here, we don't know what it is, but it can't be a 1. The 1's got to be behind the 3. And then as soon as we took the 3, the 1 became available, right? And it's not necessarily just a decreasing subsequence either. If we have like 3, 1, 2, then once we take this 3, we know the thing here has to be bigger than 3. So anything from this 3 to anything smaller than 3 will have to be, or until there's the next thing bigger than 3, this will all be its own group. And we can find those groups too. So how do we do that? So we want to find all instances. Like we want to find, yeah, we want to find, like, if we go, let's say we go backwards through the array like this, we want to find like the new next maximum. So initially the biggest thing we can get, like what's in our array? 6, 5, 4, 3, 2, 1. That's our array. So initially we want to see, okay, when do we hit the next biggest possible thing? So that's the 6. So this part right here is going to be some version of that array. Okay, now we don't have 6 in our array anymore. So now we look here. Okay, we've seen the 4, but the 4 is not going to be the next best thing. And then we see the 5, which is now the next best thing. So we remove the 5 from a list of things we're looking for, and this is a new group. Now we have this 1 and this 3. So we remove the 1, but it's not the next best. The 3 is the next best that hasn't been crossed out. So now we have this group here. And finally, we have the 2, which is the next best, so the 2 makes its own group. So now we have these groups of things, and we know each group has to be in the same array. So the question is, can we build 2 arrays that are both length n using these groups? I guess they aren't 4 long here, they're 3 long. And we can. We could do the 2 here, and then we could do the 3, 1 here. Or we could do 2, 5, 4 even. And then we could do the 3, 1, and then the 6. So yeah, that would work. So now the question is, like, just because we can partition these into 2 arrays, does that necessarily mean that everything will work fine? And it does. And the reason why is that if we look at these first indices, they will be increasing. So we'll always pick the right block each time. And then once we've picked the first right index, they'll be strictly decreasing. So we don't need to worry about it from there. So now the question is just, can we partition these things into, like, can we pick a subset of these things that sum to n? Sum to n. All right, cool. So yeah, so now you can do this in a couple ways. You can do it just with like a naive DP. So you could do a DP where you store which like thing you're at, and then what your total is. And this runs in like n squared, which I think is fine for the bounds, I believe, because n's pretty small. You can also do it with FFT. So since you know the sum of values is rather small, you can always pick the smallest 2 things and merge them, and that will keep track of how many ways, like how many ways to make each size. So we can do this for like 2 sets, and then we can merge 2 sets in order sum of sizes. So if we always pick the smallest 2 sets and merge them, like initially we'll have a bunch of sets. So in this example, we'll have 1, 2, 2, and 1. So in the first step, what we can do is we can pick these 2 1s and we can merge them. And then we'll have one group of size 2, right? So now we effectively have 3 groups of size 2 at this point. So then we'll pick the next smallest again. So we'll remove these 2 and then add a group of size 4. And then we can merge these 2. Now we have one group of size 6. So we do log n merges, or we merge each thing log n times, and then we have to do FFT on top of that, which is n times log n. I won't go into the details of this too much because most people probably don't really care that much. They just want to get the problem right. So you don't need this in order to do this. This can just improve your runtime to n log squared instead of something more complicated. Or it might actually be n log n. I'm not totally sure. I don't have like a strict bound on it. All right, couple more problems. Problem E, mastermind. So this problem was relatively doable. You can do it by like making a couple observations. So you have n+1 colors, right? And that's very useful because that means there's always some color that's never used. I guess what is the problem? So it's just like the regular mastermind game. You have some guess and you have some real, you have a real set of values that you're trying to guess, and then you have the person's guess. You get two numbers. The first is how many match exactly. The second is how many kind of match but are in the wrong position. And then you're not given the numbers that like don't exist at all. So the first thing you can do is if you have n+1 colors and there are n spaces, that means, I guess by the pigeonhole theorem, there is definitely going to be one color that's unused. So there's some like blank color that is not used in the actual answer. And or you have to print the guess, right? Or you print the answer. I guess they're the same thing. Yeah, so you're given the guess, you have to print one possible answer. So cool. So what we can do is we can like find like a garbage value. And we know one will exist. And we can do this just by iterating through, finding something that that never occurs. Just like do a count of how many times each value occurs. You do that in order n, and then find the first thing that's 0. So we can find some garbage value. Very good. Once we have that, then we could very easily at the end, we can handle the things that, like the second number, the number of right things in the wrong place. This is really easy to handle with the garbage value. So we'll have the right set of things, and then once we have that, we can very easily just replace everything else with the garbage value. So that's fine. Also, we can initially have everything in its matching position. So if this is maybe, this is what we're looking for, and we also have like some other stuff here. It doesn't really matter what this stuff is too much because we'll just replace it with garbage. So now we have some set left. Actually, let's worry about replacing stuff with garbage at the end. Maybe this is just what we have. Okay, so now initially what we can do is we can come up with like a perfectly matching version. Looks something like this. And what we want to do is like we want to move some things to the wrong position in order to have the right number of things that are in the wrong position, the correct number of things in the wrong position. So we can do this. There are a couple ways of doing this. One way is you can shift everything by n/2, which is a really smart idea that I didn't come up with. Like if you sort this by color, like it is here, if you shift everything by n/2, then that'll work as well, or that'll work. The other solution, which is what I implemented in my testing, was if you have two different things, you can look at whichever thing occurs most often, and you can take one of it and then one of something else, and you can swap them. So we can swap this blue and this green. And that will increase the number of incorrect things we have by 2. Right? We now have 2 things that are now 2 mismatches. And we want to keep increasing the number of mismatches till we have the correct number of them. So now we'll do the same thing again. Now we have 4 greens and 2 reds. So we'll pick like some pair here like this, and we can flip these. And now we'll have maybe something that looks like this. And we can keep doing this. One problem is you might have parity issues. So this will work if the answer is even, but you might have parity issues. So you might have like, you might have this case. So it's actually possible to get 3 things that don't work in this case. And you don't get that if you just take 2 and swap them. So what you can do is, in order to handle that case, this is the only case that it misses. If you have 3 things, you can take this group of 3 and you can shift them all over by 1. So if you do that, then you have a red here, a green here, and a blue here. So yeah, that's how you can do that. Then once you have that, you just want to see, okay, we've made as many inversions or as many mismatches as possible. Now we want to, for the rest of the matches, we want to just place all garbage values in the things that, in some of the matches that are left. So yeah, so basically the problem is just you want to make the mismatches, find some way of doing that, and then at the end you just replace some stuff with garbage values that's a perfect match that you don't want. Is there anything else I need to explain? Yeah, no, I think that's fine. All right. Cool. So 2 more problems, both div1. These are rather difficult, but not too bad. Let's go to contest is over. All right, so Majestic brown tree snake. So in this problem, it's quite a good problem, I think. It's very easy to understand what's going on. You've got some snake on a tree, and the snake can move either its head forward by 1 or its tail forward by 1, either direction. And the question is, can the snake rotate all the way around? Like, can the snake do a full 180 so that its tail is where its head started, and vice versa? So let's draw some tree like this. Maybe this is where the snake starts. And you've got some paths here that look like this. Yeah, so maybe this is the snake. So here's the main observation. If there's any node where it has 3 different children that all, 3 different branches out from it that are all long enough for the snake to fit in, then you can rotate the snake on that position, right? So if you have some snake like this and it's got 3 different chains that are each as long as the snake is, then you can take your snake, and your head is here. Also, your head has to be in this position. You can take your snake, and you can move your head all the way down here. Then you can move the snake like this. So let's draw like a head here. So there's the head. Then you can take the snake, and you can move the head back to here. Now the tail is here. And then we can yeah. So then it doesn't matter where, we've just reversed the snake around, and then we can leave through this 3rd position if we need to. So if we can enter from one branch, doesn't really matter what that branch is. Then we can use the other 2 to reverse and turn around, and now we can go back to wherever else we need to be in the tree. And this will effectively just reverse the snake. So we can make some moves. If we can get to this node with our head being there, then we can reverse, and then we can go somewhere else. So how do we actually how do we find these? You can do a DFS. So if you know the depth of each node, and you know the farthest depth coming from the parent, the total number of branches going out from that node that are at least the length of the snake is just sum of the number of branches in your kids going down of the length minus 1 plus, or you just check if your kid's depth is the length minus 1. If it is, you add 1 to your counter. Also, you might be able to go through your parent, so you just have to check that. So you can do 2 different DFSs through the tree, and that will handle that case. So now we know what these good nodes are, right? So which nodes are good in this example? This has 1 branch here, 2 branches here. So this node is not good. So I probably shouldn't circle it because that's a bit confusing. This node it's got this path here. It has this path here. Does this path also work? This path also does work. So in this case, there's exactly 1 good node here. So now the question is, can we have the snake's head reach some good node? And to do this, what we can do is we can split this up into a couple different trees. 1 tree at each snake node, like this. And initially, we'll have 2 pointers, 1 pointer here and 1 pointer here. And what we want to do is we want to move these pointers in. So these pointers represent where can one end of the snake be. So initially it can be in both of these positions. But now, since we have access to this tree here, we can move one head down this tree. And as we move the head down, we can move this pointer over. So we can move the head down. That will unlock new things for us to visit. Once we visit this, this has a lot of extra space, so that unlocks new room for us to visit stuff on the left. So yeah, so that's the idea. So here we can move 2 down, which means we can now unlock, I guess, all of these, right? So now once we can unlock all of these, now we can have our end at some good node, which means we've won. Cool, yeah. So basically, all this does is, like, once you have found the depths of each of these trees, like the things I've circled, then this is just an array problem. And once it's an array problem, it's very easy to handle. You don't need to worry about like LCA or any tree nonsense. It's actually pretty easy to implement. Okay, fantastic. Yeah, that's that problem. One more problem left, which is the scary seeming geometry that was dark greened by BenQ. It's not actually that bad. So I guess if you give it a chance, it's not too bad. I didn't actually try and do D when I was VPing it. I did E instead, and I just ran out of time implementing it. But I had the intended solution. I just couldn't finish typing. All right, so in this problem, you're given some origami sheet of paper. And now the question is, if you have this origami sheet and you fold it along some dotted line, then it'll look like this maybe. The question is, what is the area, excuse me, of this shape? So the new shape will look like, I'll outline it in green. It'll look like this. And this isn't a particularly interesting case because it's just the area of the shape to the left of the line. But you can imagine that if it looks slightly different, this part might come out like this, right? So now we have to add some extra amount for this space right here. So okay, how do you actually like do this in a like plausible way? Here's the idea. So maybe this is your shape, right? Instead of trying to like reflect it over its own line, what we can imagine is, let's say we have some other shape that's like the exact same, but it's just mirrored across this line here. And now what we're going to do is we're going to take this first shape and we're going to move it over. So after we move it over by a bit, then we'll have something that looks like this. Roughly. It's a little off. But so now if we look at this overlap, half of this overlap will be the area that's deleted by the fold, right? All of this overlap represents, like, if you look at half of it, now this left half here is what the paper is going to look like. So what we care about is, what is this area where the paper is too thick? It'll never be more than too thick. It's either 1 or 2 thick in all places. So we just care, what is the area where it's too thick? And now the final area of the new shape is going to be the area of the original paper minus where it's too thick. So that's just this space right here. So how do we find that? So now the one issue is we have a bunch of queries, which makes it a bit tricky, but we can handle that. So it's not too bad, I don't think. And yeah, okay. So how do we do that? So if you've got some polygon, we know it's monotonic, which is very nice. And what we can do is we can actually take and we can split it up into these sections like this. So if we split it up into these sections, all of these are going to be like negative copies of its area. And now I'll draw these in blue. These will all be positive. You can imagine these are like infinite trapezoids, or like not necessarily infinite, but trapezoids to some line very far out. Now, since the x-coordinates actually go in different directions, they go one direction here, one direction here. The implementation-wise, you don't even have to treat them separately. I was trying to treat them separately and it got messy, but you don't even need to, which makes it easier. Now, okay, on top of that, we need to find the intersection between two of these, right? So we have two of these now. We've got one for this side. We also have another one for this side. Looks something like this. This is it's hard to draw things in weird. I'm not very good at it. Yeah, I think it's like that. There you go. That's almost right. So now the idea is we want to find the intersection here. Well, really, since we have it split up into trapezoids now, all we have to do is find the intersection between two trapezoids, and then we can do a sweep down and see, okay, like check these adjacent pairs. What's this intersection plus this intersection? So how do we do this subproblem now, which is just the intersection of two trapezoids? That's all we have it removed down to. But we also have to like answer queries, which is tricky. So okay, so hang on. So give me a sec here. So if we've got these two trapezoids, what we can do is we can split this up into just this interesting area, right? So we can cut all the trapezoids. Now we have trapezoids whose whose y's aren't significant, right? We just know the thickness, and we have these two lines. Okay, so what do we turn this into? We turn this into something that looks like this. We want to find the intersection of these two trapezoids that have the same height here and here. We want to find the intersection if we slide them over some amount. And this is just a line, right? So initially it's going to be 0 for some point. The graph of this will look like this. It'll be 0 for some prefix. Then it'll increase linearly for some amount of time. Then it'll be just the max value for some other prefix, right? Or
good night, sir.
It'll be, yeah, that's not true. So like this is the amount it increases by. This is the delta for some given y. Yeah, so then I guess like the other version is it would be kind of parabolic. So initially it would be 0. Then it would increase like this, and then it would be linear like that. So this is where like this part is a parabola from here to here. It's a parabola. Yeah. Yeah, I don't think that's super important. But here's the, I'm not going to walk through all of the math because I think it would get quite boring. But the important part is like we know the event where this starts, and then we know like what the initial delta would be. And then we also know when this will hit this, right? So we know that time event as well. And we can process all of our queries in order of how far you need to move one of the polygons. In other words, how far we're moving these trapezoids. And we just need to figure out if we move it by this amount, what is the total area of intersection, which we can handle because they're like a whole bunch of trapezoids. We can handle that by doing an event sweep for when each of these events changes, like when the delta changes in a meaningful way. All right, so that was kind of difficult to explain. I probably could have done a better job explaining that, but oh well. The editorial is quite nice, and then Monogon's solution for it is also very, very clean. So would recommend that. So anyway, I hope you enjoyed the problem set. I thought it was very good. Remember to upvote Monogon's editorial, give him contribution, because he certainly deserves it. They're very interesting problems, I thought. So yeah, I hope you enjoyed the contest. That's all. Goodbye.